All right, so hopefully we're on the same page here. You're getting very similar numbers. Remember, for your means, you just use your average function. In this case, the first column has data in A3 to A33. For your standard deviations, you'll use the stdev function. So this is B3 out to B33 for the y variables. Now, in terms of counting your sample size, we do want to use count, but we don't want to select all of our data. We just want to select one column. Because remember, our sample size, as we're interpreting it for the correlation coefficient, is just the number of rows. So if we were to select both columns, we would double count the number of rows. So just select one column, do your count. We have a sample size here of 31. Okay, we're now ready to compute the z-scores for each one of our x and y columns. So again, pause the video, give yourself a chance to self-test here, and compute these z-scores using fill-down formulas. All right, so the key thing to remember here is that when we're doing our fill-down formula, we have to make sure that we fix, using our dollar signs, the subtraction of the mean and the division of our standard deviation. These cells that I put in the dollar signs, I do not want to update. I don't want x bar or s of x to update. What I do want is A3 to update, so that when I drag this thing down, I end up getting z-scores. All right, so I'll drag this down. I'll take it down to 33. So I have all the z-scores for my different x measurements. And now I'm going to do the same thing for y. So measurement minus y mean fixed divided by y standard deviation fixed. And remember, if you're on a Mac, you can hit Command T to put the dollar signs in automatically. And if you're on a PC, I believe it's the function button in F4. All right, hitting enter. Now that we have data to the left, I can just double click this to fill it down to row 33. All right, and now we have our z-scores written out. Now, according to the formula, the next thing we have to do is multiply these two z-scores before we sum them up. So in our next column, let's write a cell referencing formula that will take the product of your z-score for x and your z-score for y for the given row. So pause the video, try this again on your own, see if you can think of a nice cell referencing function to do this, or formula to do this. All right, pretty straightforward. We want both of these to update as we drag them down, so we're really just going to take d3 times e3, and then when we drag this down, the next cell down will be d4 times e4, d5 times e5, etc. We now have the product of all of these summations. I'm going to move my formula over here. Now the next step is, now that we have this product of z-scores, we want to sum them all up. So that's what I'm going to put here. We can use our sum function to do this. F3, remember our last row is 33, so I can just sum this range. And that's going to be the numerator of my Pearson correlation coefficient. It seems really big, and that's because we haven't divided out by the n-1 yet. But I just want to remind you of the prediction we were going to make. Since our scatter plot showed that these dots kind of follow fairly closely a positive sloping line, remember our prediction here is that this should be positive and close to 1. The close to 1 indicates that it follows the line very closely. In other words, the dots aren't very spread out. So let's see what we get when we take cell reference that big summation in the top and we divide by our n-1. Or you could just divide by 30, that's fine too. What's our Pearson correlation coefficient? 0.89. Pretty good. Not only is it positive, but it's also close to 1. So this is sort of behaving the way that we would expect it to. The last thing that I want to cover very quickly is the short way to do this. Obviously, we're not going to create a column of z-scores, multiply them, sum them up, divide by n-1 every time we want to find a correlation coefficient. So what we're going to do instead, I'm very quickly going to show you the shortcut formula for doing this. And this is why I've been making such a point to call this the Pearson correlation coefficient. It's really just a reminder that the Pearson command in Excel will give you the shortcut for computing this correlation coefficient. So let's see that we get the same values. I'm going to shrink this chart a little bit. And in the cell below, I'm just going to do equals Pearson. And it's going to prompt me for two arrays, and these are just the arrays for the two variables that I'm trying to compare. So my x variable is A3 to A33. My y variable is going to be B3 to B33. And when I hit enter, I'll get exactly the same correlation coefficient as we computed the longer way. The last thing I want to discuss here is something called the R-squared value. We're going to be talking about this in a lot more detail when we discuss linear regressions. But one of the benefits of the R-squared value, it literally is your Pearson correlation coefficient, which we denote R, squared. One of the benefits of the R-squared value is it's strictly a measure of strength. Keep in mind that correlation is a measure of direction in strength. If it's negative, you can still have a strong negative relationship between the variables. When you square your correlation coefficient, whether it's a negative or a positive relationship, the sign will become the same. Your R-squared value is always positive. And so what it does is it kind of takes the strength measurement from your correlation coefficient and sort of removes the direction of the relationship. So R-squared is a nice way to look at just the strength of the relationship. And the general note for this, closer R-squared is to 1, the better the fit. And what I mean by this is the dots are closer to the line. All right. In fact, if you get an R-squared value that's exactly equal to 1, your dots are perfectly following a line. Okay, I want to give you a chance to practice creating some scatter plots and computing some correlation coefficients with this Pearson function. So here what I have are 3 different variables. We'll call them x, y, and z. And what I want you to do is for each one of these, I want you to compute the Pearson correlation coefficient for the pair identified. So do this for x and y. Maybe do that here. Do this for x and z. And do this for y and z. And then we're going to answer the following questions afterwards. We'll deal with the significance in a second. You don't have to worry about that right now. So find the correlation coefficient for x, y, x, z, and y and z. And then I also want you to take the time to actually plot your scatter plots for each one of these 3 pairings. Okay? So pause the video at this point, and this is probably going to take you maybe 5 to 10 minutes. And I want you to walk through, do the Pearson correlation coefficient computations first, and then walk through, and then let's take a look at the visuals for each one of those 3 possible pairings. All right, I've stopped short of doing the scatter plots because I want to take a look at these correlation coefficients and use them to make a little bit of a prediction. All right, so first of all, just looking at the magnitude, and what I mean by this is I'm ignoring whether this is positive or negative. The relationship between y and z has the largest magnitude. It's incredibly close to 1. So when I think about this scatter plot for y and z, I'm going to expect these dots to be very closely following a line. The relationship between x and z seems to be the weakest of the 3 because it has the smallest magnitude. And x and y is going to be just slightly stronger than x and z. So for these 2 scatter plots, I'm going to expect the dots to be more or less following a line, but there's going to be more variation, more of a spread. The other thing I want to note is that the relationship between x and y has a positive correlation coefficient. So these dots should, typically speaking, follow an upward sloping direction. X and z and y and z, however, are negative correlations, so they should have a downward sloping direction as we move to the right. So I plotted 2 of the 3 scatter plots. Let's start with the xy pairing. This had the weaker of one of the weaker correlation coefficients, but it was positive. And we'll notice that there is quite a bit of spread for these dots, but the general trend here is that as x increases, so does y. So this is our positive, less strong correlation. Now, the correlation between y and z, which is our second plot over here, is very strong, right? The magnitude's very close to 1, but negative. So we'll notice that these dots very tightly follow a negative sloping line. I wanted to do x and z together, just because I figured some of you may have gotten stumped on how do you select two columns that are next to one another. Remember, at the beginning of the year, we kind of discussed how to use this selection bar up at the top here, where if you type in ranges like A2 to A33 and you separate with a comma C2 to C33, it'll automatically highlight the cells that correspond to those ranges. So anytime you want to make a jump or a break in the rectangle, you just separate with a comma. So again, I took A2 to A33. That would be just my x values. And then I used a comma and typed out C2 to C33. And when I hit enter, I highlight the data I want. So now I can do my insert scatter plot. I can change my chart title. This is Z versus X. We typically put the one on the vertical axis first. This is Z versus X, and I'll shrink it down so that I can see it a little bit. Once again, this had sort of a magnitude not very close to 1, so we see quite a bit of spread out from our dots, but it does have this negative relationship. It seems to be going down as we move to the right. Now, if you are interested in changing colors, you can do this from the chart design. You can just kind of select a different palette. So sometimes if you're doing a bunch of these, it's nice to use different colors, so it's easier to spot the differences between them. All right, so I want to move these scatter plots off to the side so I can answer some of the questions below. So first of all, are x and y positively correlated? The answer here would be yes, because r is a positive 0.62. Right? And what does this mean? Well, it essentially means that typically speaking, when x increases, so does y. So if you have very large x values, your y values tend to be large as well. Which two variables exhibit the strongest linear relationship? Pause the video and try this one on your own. Since strength, i.e. not direction, depends only on, spelling errors here, depends only on the magnitude of the correlation coefficient. The relationship between y and z is strongest. Right? It has the largest magnitude. If you ignore the sign, it's the value that's biggest at a 0.982. And visually, the way that plays out is the dots are the closest to this kind of line that appears to be describing the relationship between the two variables. All right, now to get our last question, we have these x and y and x and z. We have these kind of follow-up questions. Are these significant? What does that mean exactly? That's what I want to address next, and we'll come back to this particular worksheet and answer the question.